Well, hello and welcome back to Electrical Fundamentals Engineering 202. We want to look at experiment number 3 today, and I will put this up here so you can hopefully kind of see what we've got going. I realize this may be a little bit difficult to see on the camera, but you have this in hard copy form. So we've got a circuit here, and what we're most interested in this circuit is to the right of this line, or this point right here. So we've got a branch with an inductor and a resistor, and then a branch with a capacitor and a variable resistor and a resistor. And if you go back to my opening comments of lecture 10, you'll see where I talk about coming up with the impedance for this and predicting what this Rx, this variable resistor, needs to be so that this has a power factor of unity, so that there's no phase shift in the impedance here, so that the inductance and capacitance is balanced. And we're going to try and tackle that experimentally. I had to switch out my power supply, so I'm changing this V1 from 10, I think in your pre-calcs you probably saw this 10 to 12 volts peak to peak. I'm going to be running close to 20 volts peak to peak because I'm just going through a transformer, but that's fine, and I'll try and update that for you. And then we'll look at these other values too as we go. You would have got an email from me about a week ago talking about this pre-lab calculation. That's going to be important for you to do. In fact, I'm not going to tell you what this resistance turns out to be until you share with me what your pre-lab calculation is based on the actual values of the elements that I will share with you today. And then we'll look at the questions kind of as we get through this. I think those will be fairly easy to answer. Well, this is the circuit on paper. Let's look at it a little more, how it lays out on this thing. If I were to try and diagram this a little more, what's happening here, I've got something like this. And I want to talk a little more, the last couple labs I haven't talked too much about the specifics of the elements themselves and whatnot. I wanted to spend a little more time talking about that. So let's get into that. This resistor up here, that's supposed to be a, let me double check my notes here, 1 k ohm. We'll measure it, get that exact value. And like I said, we're not, that's really just for protection. We're more interested in this portion right there. Then the capacitor, we're just going to take it as its face value of 25 microfarads, although I believe it's plus or minus 20%, so that could vary quite a bit. The inductor, we're going to be at a half a Henry, 500 millihenries, and we'll just take that at the face value. And then R2 is 100 ohms, and that's really mainly a place to put all of the internal resistance of that inductor there, and we'll measure that so that we can deal with that also. And finally this R3, 100 ohms there, and we'll measure that. I've got the potentiometer. We could have put in a potentiometer something like this. You've used these before. We just use the middle leg and one of the outside legs, so maybe these two legs here, the orange and the black, that would work out fine for us. I've actually used the built-in potentiometer here. It'll be a little more convenient, so I've shown that we come down with the wires there and use that potentiometer. One thing, and again, I'm going to spend a little more time in this lab pointing out some of these tricks and tips and things that you should know as you spend more and more time around these things. The capacitor, we're actually using a capacitor here that if you look at it, it's kind of probably hard to see there, but there's a little groove here and there's a little groove right there. That means it's non-polarized, so either end is the same. You could switch this around either way if you wanted to. But if you get into dealing with one that has a groove on just one end, that's going to be the positive end. So when you have the groove or the line, sometimes there'll just be a line there. That usually indicates the positive end, and the one that doesn't have it is the negative end, and you want to put those in. This would be the positive side here. So let's go about getting those values. Let me turn this power off on this thing, and I'm going to go ahead and unhook this. And remember to measure resistance. We always need to unhook one end of the resistor, so try not to get too much in your way here. Put one probe there and one probe there. Of course, I've got the line in your way. there we go. So 982 ohms. It's saying 0.982 k ohms, so we'll just say 982 ohms. 982 ohms, I'll record that. And put back what I've disconnected here. And like I was saying on the source, and the source is actually off screen, this designer has a built-in power supply, and it's kind of nice because you can adjust the waveform and whatnot. And I was having a lot of trouble with it at the lower frequency. These circuits were designed for different power supplies that we had in lab. Obviously, we're not in lab anymore. So probably to really do this, I'd need to redesign the circuit, but I opted just to change my power supply, and this designer has a built-in transformer, a lot like a doorbell transformer or something like that. So I just used that. It's not near as nice, it's not as adjustable, it's not as clean, but it's pretty robust and it seems to be working for us. So I'll show you some of the good and bad of that as we go on. So if we look at that, that's our R1, and then like I said, our capacitor, that's 25 microfarads plus or minus 20%. So I'll jot that down here, 25 microfarads plus or minus 20%. Then we come over right in here. In this area here, you would have the inductor, but I couldn't fit it in there, so I've jumped it over. I go from this green cable, almost off camera here. See if I can get that in there a little more. The green cable's coming over to this. This is 500 millihenries. There's a whole bunch of inductors on this board. It goes from very small values of inductors up to the largest one, 500 millihenries. And then the red one back over to here. So it's very much like taking this and putting it right in there. Although we don't want to do that. We don't want to leave it on the board. We put these on the board so when we do use them in the lab, they don't get hurt. So the one thing that I'm going to do is unhook this inductor. I'm just going to take the inductance as a half of a Henry, 500 millihenries, but I would like to measure the resistance. And this is the same one that we used in the first lab. So you should probably recognize that number, 565 ohms, 0.565 k ohms. So we'll say 565 ohms. Okay, I'll hook that back up since I'm done measuring the resistance. Then I want to come down here to these resistors. This resistor is R2. So I think if I just unhook that, I can get it isolated. Remember, this should be about 100. And it is 99.5. Got my hands in the way there, sorry. 99.4. Not sure what's beeping at me. I think this is so 99.4 ohms. I'll hook that back up. Then this guy here, this is my potentiometer. We'll measure that later. I'll unhook that. I'll measure across here. That's 100.8, 100.7, 100.6, 0.5. We'll call it 100.4. And I'll hook that back up there. Okay, so I think, with the exception of the input voltage, we have most of the values that we need here. So I'll put this up here. And like I said, I'm not going to put together a document and share these with you. I'll just share them right here on the video to encourage people to watch the video. So this R1 we really don't need, but just for completeness sake, 982 ohms. Then this inductor, half a Henry. And then the big thing there is the internal resistance, 565 ohms. That's huge. So you're going to have to, in your calculations, take this R2, and you're probably going to change this R2. It's not going to have the value of 99.4, but rather it's going to have the value of 99.4 plus this 565. Okay, so put your internal resistance here, add it to that so that you have it accounted for. The capacitor, 25 microfarads, plus or minus 20%. So in your calculations, you could play around with that as we try and justify, did we get pretty close to our experimental value? This is our potentiometer, like I say. We'll measure that a little bit later. And finally, this R3, you've got 100.4 ohms right there. And in your calculations, I actually separated and had this RX right here and R3, but some people choose to combine this all into RX, and just to make your calculations a little easier. So with those values, let's go ahead and fire this thing up and see if we can take our data and get on with this. So make a quick double check on my connections there. I think we're pretty good. And yeah, that looks like what we're looking for. So the yellow band here corresponds to the yellow that you can kind of see. And I realize trying to get the whole circuit in here, we get everything in the picture, but nothing's really great, and I do apologize for that. But the little details I will try and point out, so if you have a hard time seeing them, I'll get those somehow read into the record. But when you fire up the oscilloscope, a few things, it actually has an internal calibration area right here. Maybe I'll point with the old red pin here. You can hook this up and you can calibrate the probes. Usually if you go into a lab setting like we'd normally be in, they don't want you messing with the calibration there. They've got them set up. You leave the probes with the oscilloscope and everything is set. But just pointing that out as you maybe think about going in and starting to use an oscilloscope on your own. We have channel 1, that's the yellow one. We have channel 2, that's the blue one. Yellow one being larger, bluer one being smaller. We need to keep track of the scales here. Our scale for the channel 1, 5 volts per division. Channel 2 is 2 volts per division. And we use this knob here to control the magnification, like that. Okay. And then this is the time base. And they're usually, you look at any oscilloscope and it's usually arranged this way. It'll have channel 1, it'll have channel 2. It might be multi-channel, but if it's 2 channels, very common. Channel 1 here, channel 2 here, and then your time base. You can control your magnification in the horizontal. Okay, like that. So when you walk up to the oscilloscope, a lot of times it may be something like this, and there's a few ways to make sure that you're comparing apples to apples. What we want to do is we want to get these to reference this line right here. So a couple things that we can do. If I look at the menu here, I probably want to have both of these on AC. Look at the channel 2 menu, put those on AC. That's probably good. And then you could actually, and when I had the menu up, what you could do is you could have grounded that, and I can just do that. When you ground that, it goes down to 0, and then you could put that on the line there. Well, this is kind of a neat scope. I don't know that's a particularly reliable scope, but it's got a lot of features on it. So I'm going to turn this back to AC and get rid of the menu. These buttons, where you move it up and down, if you just press on them, it will automatically put it at 0 for you. Let's do that. Okay, so now I have those zeroed and I can start to trust that. Okay. The other thing is, let me turn off this channel 2. So if I'm looking just at channel 1, and this is where I was saying that I'm using a little different source and I've got a little more voltage there than I was talking about, it looks like I am at about 2 divisions and 5 volts per division, so I'm going to be, what, 10 volts for my amplitude, so about 20 volts, close to 20 volts peak to peak. It looks like it's not perfectly centered, but that's okay. That could be in the source. That's not going to change where they cross necessarily. If I want to double check that, I could go to this thing. I could look at grounding that. Come on, ground, you guy. Oh, sorry. That's channel 2. Channel 1 menu. There we go. There's the ground. And you can see that we're right on there. Okay, so any deviation is probably coming from our source, and that's not uncommon. So let's turn this back to AC. Get rid of that. We'll bring channel 2 up there so that we can look at them. And make sure that that's 0. Make sure that that's 0. We're running at 60 hertz. That is the nice thing about the transformer that I'm running for. We know it's going to be 60 hertz. There's no deviation there. So I would put that in here. 60 hertz, which is going to be what, 377 radians per second. So I'll record that, 60 hertz, 377 radians per second. So that'll be important when you need the frequency. So now what the whole experiment is about, and this is kind of the cool part about this, is by changing this potentiometer. So I'm just twisting this knob here. All this is a potentiometer. It's just one of these, but it's built in. I can, and you can see, you can actually get these lines to move. Okay, so it looks like now the blue is ahead of the yellow. If I go back this way, the blue is behind the yellow. So it goes from leading to lagging. So the circuit is going from more inductive to more capacitive, or vice versa. Okay, so what we want to do is we want to try and figure out where those cross, where there's 0 phase shift. And you might say, well, that's about it. And you're probably, screaming at the screen at home saying, I can't see that on the oscilloscope. Well, in real life right here, I'm actually having a hard time seeing it. So let's do something to improve not only my position, but hopefully your position. I think we can tell where those things cross a lot better if we make the lines more vertical. So I'm just going to change the scale. I'm not changing the parameters of the circuit. I'm just changing my measurement tool here. So I'm going to make those lines more vertical. And then let's zoom in so I just see one of them. So now I'm looking right here, and maybe I'll even zoom you in. Okay. Yeah, maybe I'll change it just a little bit there. So I'll just take you off here and hold it. Okay. Try not to get too much glare. Wonder if we can get rid of the glare there. Okay, great. Okay, bear with me here, man. Sorry for making you sick. But you can see I haven't adjusted my potentiometer, and it's obvious that we are not crossed very well. So I'm not multi-talented with doing 2 things at once here. But let's see if I can do this. I'll hold the camera and I'll adjust these. Okay, and you can see that goes back and forth. Let me move this horizontally a little, get it away from that origin so I can see it a little better. Okay, that looks like the blue's ahead. There it's behind. So right there. And if you can see that I can move this knob quite a bit. So as I move this knob's moving quite a bit. Okay, so there's going to be quite a bit of range. There's going to probably be a fair amount of error in this thing, is what I'm getting at. But let's come down here and really pay attention to this. Let's see if I can. I would say that that's crossed pretty nicely right there. Well, let me put you back here before I make everyone sick. I think that's okay. We'll turn this light on. So now what I need to do is I need to measure this resistance here. So I'll go ahead and turn that off, and then I'm going to pull this wire out here so that I can now measure across the potentiometer. You have to unhook one leg of the potentiometer to do that. And this is where I want you to do those pre-calculations. I want you to take these numbers that we have here, to put them in your calculation tool, and to come up with what you think Rx should be. So I'm actually going to move my the volt ohm meter off of the screen, because I don't want you to see what the answer is. Because what you're going to do is you're going to email me with what your calculated value is, and I'm going to say, yeah, that's great, and it should be right on because it's calculated, right? Okay, so I'll say, yeah, that's what I got, and then I will share with you what we measured. Okay, so if you want to find out what we measured, you have to share with me what you calculated. Just do it by email, that's fine. Okay, so you don't want to wait till midnight the night before this thing's due, because I'm probably not going to be there to answer your email. But in the next few days, run the calculations, email me what your calculated value was. Hopefully it's right, and then I'll give you what the measured value was. If it's not right, I'll tell you, yeah, I think you're a little off this way or that way, and we'll get you through the calculations. And don't think that I'm picking on you, because we're doing this differently. This is what I did in face-to-face labs. We didn't let students start building this thing and putting it together until they had the calculated value and they kind of knew what they were going to expect. Well, let me go ahead and make this measurement here. I have to concentrate not to blurt it out. That's about what I was expecting, so that's good. Okay, so like I say, when you run your calculations, when you take these numbers and run your calculation, tell me what you get for Rx, then I will share with you what I measured. Well, let me put this thing back together like that, and we'll turn it on. And you notice that the probe position here has been across this resistor. Okay, and I will maybe run these back down so we can see the waves a little easier. This should be okay. Okay, so we'll get something like that. Okay, so you can see that those waves are definitely in phase. Okay, and again, if the photo quality is a little bit poor, I haven't adjusted the potentiometer. I haven't changed the potentiometer, so they should be nicely crossed. And probably the reason the photo quality is kind of low is because they are literally one on top of the other. If I change the magnification, there we go, but you can see that they are crossing at the same point. Okay, and the probe position is here. It's measuring across this R1. Okay, so back over here on this diagram, I have the channel 1 right here. I have channel 2 right there. Well, one of the steps in the procedure, if you've looked at it, says to come in and put a probe right here, and then also put a probe right there at points 3 and 4 if we go back to the original schematic. So let's do that. So before I move these, they are definitely in phase. Well, let me move them. So I'm going to put channel 1 over here. I can just do this like that. And then I'm going to put channel 2 right there. So I've got channel 1 right here, I've got channel 2 right there. There's smaller voltage values for sure. Let's see if we, there we go, we got it. We grabbed the image there. So what do you notice? Well, they're definitely way out of phase. Okay, they're way out of phase. So what do we take away from this? Well, with this potentiometer, we balanced the entire circuit. The entire circuit appears to be resistive, that the inductance and the capacitance are canceling each other out. But if we look in more detail, if we go and we look at the individual branches, okay, so before we were measuring across here, we were measuring this whole circuit. But now when we're looking at these individual branches, they're wildly out of phase, aren't they? Okay? They're wildly out of phase. I always use this example, and it seems like we're becoming more politically polarized, so sooner or later it'll get me in trouble. But let's say we're going to go to a political rally, and we got a bus, and we put 10 really hardcore right-wing people on the bus, and we put 10 really hardcore left-wing people on the bus. Well, if we looked at the entire bus, what would we have? We'd have something that was fairly neutral, right? Okay, the bus taken as a whole, their political disposition would be neutral. But if we took any one person out of the bus, what would they be? They would not be neutral at all. They'd be radical on one side or the other. Okay, so you can think about it a little bit that way if that political analogy distresses you. There's other analogies that you might be able to think of. Well, let's see if we can get through the questions or wrap this thing up. And again, you've got this in hard copy form. So let's look at the question. Based on your calculations, what value of Rx gives you a power factor of unity? Okay, power factor of unity, phase shift equal to 0. I could say it in a lot of different ways. We could even probably talk, next term we'll be talking about resonance. Sorry about that, I think that's the ohm meter buzzing. So this is the Rx, that's your calculated value. Okay, so you're going to take these values here, the internal resistance of the inductor combined with R2, that actual value there, and so forth, the 60 hertz, and you'll run the calculations on those and come up with your calculated value of Rx. What value of Rx gave you a power factor of unity in your measured circuit? Okay, so when you email me and say, hey, my calculated value of Rx is this, if you get it right, then I will say, well, hey, great, the one that we measured is this. Okay, you'll be able to put that there. And then, are they the same? My guess is they're probably not going to be the same. Your calculated one is going to be an ideal one. The measured one is probably going to be what's off. What could be off with that? Okay, and you can, you know, if they're close to the same, I'd say they are the same. Considering experimental parameters, you could say they're the same. Or you might say, no, they're not the same, but they may be not as far off as they might appear because, well, what's going to be the because? Well, remember with your capacitor, you could be plus or minus 20%. So if you get a nice Excel spreadsheet working, you could play around with that a little bit and see how much that changes it. The other thing, and this is one of those things that's unfortunate that you're not here twisting the knobs, but I was trying to show you, as I was holding the camera and twisting this and trying to look at the oscilloscope at the same time, that you could twist the potentiometer quite a bit. Okay, if you ever maybe tuned in a radio station in an old analog radio, you can have the tuner. There's quite a range for the tuner that station still comes in. Same thing here. There's quite a range for this resistance that it appears to cross on the oscilloscope. So I think those are that is probably the biggest place for error. And let's see. In one sentence, what did you learn in step number 3? Step number 3 is where we moved these probes from measuring the entire circuit as a whole and started to look at the individual branches. And I gave you an analogy for that. Hopefully you can put that in a nice sentence. So I think that gets us pretty well wrapped up. And like I said, do those calculations. Shoot me an email with what your calculated value of Rx should be. And then if it's right, I will share what the measured value was. If it wasn't right, I'll try and give you some hints on how to maybe get it right, and you'll hopefully come back with the right number. So, like I said, kind of a fun experiment. We got to actually see this circuit go from being predominantly capacitive to being predominantly inductive, and vice versa, as we watch these lines on the oscilloscope go back and forth. So I will leave you with that. Thanks for watching. Take care till next time, and when we get back in lab, have a good one.